Piezo resistance measurement will be our first topic of the day. Piezo-resistive sensing has gained widespread use in MEMS sensors due to the ease at which we can convert a change in mechanical stress into an electrical signal. So the most straightforward and obvious way of performing a piezo resistance measurement would be to simply apply some bias current, which I'm going to call IDC, to our piezo resistor, which will have some nominal resistance R naught, and then we'll have some change away from that nominal resistance due to an applied stress. And our output voltage is simply the voltage drop across our resistor. So using Ohm's law, what we'll have is an output voltage V out that is equal to our current IDC times our resistor value R naught plus delta R, which could be written as IDC times R naught plus IDC times delta R, or IDC R naught plus IDC R naught times pi L TL plus pi T T T, like so. So we have some portion of our output signal that is just a DC quantity. So this is what we would normally have. And then we also have this bit over here that represents the change in our DC level when we have an applied stress. So our output signal here is proportional to our applied stress T. Okay. The power consumed by this measurement system is going to be simply IDC squared times our nominal resistance R naught. And this measurement system will have a noise voltage spectral density of Vn is equal to the square root of 4 kBT times R naught. Okay. I'm bringing these things up because we're going to look at a couple of other different schemes, which may offer better performance, but the trade-off there may have something to do with noise relationships or power relationships. Okay. Excuse me. So while this type of resistance measurement scheme is useful in some applications, there are some disadvantages to it. Because the change in resistance may be very small, it might be necessary for us to amplify things. Well, right now, our signal resistance, that small portion that's proportional to our applied stress, and our DC offset are effectively linked together. So we can't amplify just the small signal. We would also wind up amplifying that DC level as well. And that is problematic because it would require supply voltages for our amplifier to potentially up to hundreds of volts in order to make that work, which is not going to be acceptable for a small scale system. Another problem we've addressed previously is the temperature dependence of the nominal resistance R naught may be greater than the piezo resistive effect as well. So that would require costly calibration processes to eliminate that temperature dependency to get accurate signal measurement. So like I said, this simple resistance measurement will work for some applications, but we may have to take into account other things. So the most obvious change we could make would be doing ratiometric measurement, right? So we could start with a single-ended ratiometric measurement, also known as our good old voltage divider circuit. So let's call this single-ended sensing with, sorry, this should be over here, a bias voltage. And this type of sensing scheme would look something like this. So we have some DC voltage here. We have a nominal resistance R naught. And then here we have our piezo resistance R naught plus delta R. And this is the node at which we measure our output voltage. So one quick thing here regarding the development of a circuit like this, typically speaking, we create our reference resistor R naught by itself while we create our piezo resistor, and we just implement that reference resistor in a place that we do not expect any stress or strain to occur. So you would do that beyond the anchor point into the bulk of the material that isn't going to undergo any mechanical deformation. Right. All right, so we can use voltage division to figure out what our output signal will be. And we're going to have quantity V out that will equal to our DC voltage VDC multiplied by R naught plus delta R over twice R naught plus delta R. And since delta R is typically much smaller than the quantity R naught, we can use a Taylor series expansion to more simply relate this to our applied stress. So using a Taylor series expansion on the above expression, we are going to get VDC times 1/2 plus 1/4 delta R over R naught plus our higher order terms. And we are going to effectively just neglect those higher order terms. In doing so, we get an output signal of 1/2 VDC plus 1/4 pi L TL plus pi T TT times VDC. So we have effectively eliminated one of our problems here, all right? So the problem that we have eliminated is, since our signal resistance, or our output signal, our output signal no longer depends on the absolute value of the quantity R naught, right? So as long as our reference resistor R naught and our piezo resistor, our working resistance R naught plus delta R, as long as they are at the same temperature, exhibit the same temperature dependency, which means if we fabricate them at the same time out of the same material, that should be true. Our temperature dependency of that resistance is canceled to the first order. So the temperature problem largely goes away. The fractional change in resistance still exhibits the 1/T temperature dependency of the piezo resistive coefficient pi. We can only get rid of that by electronic compensation, but it's not nearly as bad as if we didn't have that reference resistance in there. Okay. Our DC power consumed by this system is just going to be V DC squared divided by twice R naught, which it's hard to compare that to our DC bias current system a moment ago, since we're using a bias voltage in this case, but we'll come back to this in a moment. Our noise spectral density, however, is going to be Vn will be the square root of 4 kBt. So what's the equivalent resistance that we see looking into the output node? So if we wanted to find the Thevenin equivalent resistance, and we're going to throw away the delta R because we're just looking at our DC or our average power consumption here, I would argue that we see an R naught looking down and an R naught looking up, both the small signal grounds effectively. So we see those two resistors in parallel. Okay. So from the power perspective, we have a total voltage drop of VDC over those two resistors in series. But I am arguing that our output noise spectral density, we would use the equivalent resistance we have looking in to that output terminal, looking at a dead network. And so this is going to look like 4 kBt times R naught in parallel with R naught, or 2 kBt R naught. So not only do we eliminate our temperature dependency, we also generate half as much thermal noise at the output. Okay. So this is an advantageous scheme. Okay. We still have the problem that we can't really amplify our output signal. And if we notice here, our applied stress is scaled by a factor of 1/4 VDC. So it's inherently going to be significantly smaller than the DC contribution, right? So if we want to get rid of that DC component, what we can do is use a Wheatstone bridge configuration. Okay, and there are a couple of different Wheatstone bridge configurations that we are going to look at. Let's go to the next page here. So let's call this differential sensing with a bias voltage. And we're going to have two different cases, I think, that we're going to look at here. So our first is our simple Wheatstone bridge. Yeah. Making sure I'm putting my resistor in the right place. If I put it in the wrong place, the only thing that would change would be the sign. Or differential. So we're going to have R naught, R naught, R naught, and then down here in the bottom right, let's call this guy the R naught plus delta R. Here's our voltage V2. Here's our voltage V1. And using our previous results, it should be fairly obvious to see that the quantity V2 is going to be 1/2 VDC plus 1/4 pi L TL plus pi T TT times VDC. So effectively, the right-hand side is exactly the same as the voltage divider that we just used, or we just analyzed. Our left-hand side, V1, is going to be VDC times R naught over twice R naught, which is just half of VDC. And so our differential output, V2 minus V1, is just going to be 1/4, or I guess I should write approximately here, since this does utilize a Taylor series expansion to get this result. 1/4 pi L TL plus pi T TT multiplied by our bias voltage. So by using this double-ended ratiometric sensing, or more commonly known as a Wheatstone bridge, our output signal no longer has a DC component that would be amplified should we send our output signal into an amplifier. Okay. Now, let's talk about our power relationship here. So what's the resistance that I see looking down effectively from our DC supply? So I would argue that we have 2R naught in parallel with 2R naught, which looks like R naught. Exactly right. I'm sorry, what? So V2 minus V1 is what we would consider the output voltage of this system, because we're looking at a differential measurement. So let me. That makes it more clear. So if we take our output signal to be the difference between those two nodes, it winds up eliminating that DC contribution from our output signal, right? So let me scroll back up here. So what we have right here is literally just the right-hand part of that Wheatstone bridge. And in doing so, we have, in taking our output in this way, we have a DC contribution to our output signal, and then a small contribution that is due to our applied stress. Using this Wheatstone bridge configuration and taking our output to be V2, the output on the right-hand branch, minus V1, the output on the left-hand branch, eliminates that DC component so that our total output signal is proportional to our applied strain, or our applied stress. So this is just a measurement technique to get rid of that DC offset voltage, which is problematic if we need to amplify our output signal. Okay. So our power relationship is going to be VDC squared over twice R naught in parallel with twice R naught, which is just VDC squared divided by R naught. So we consume twice as much power, which makes sense because we have twice as many resistors as the last scheme. We also wind up observing twice as much noise. So if we looked at the output resistance from the V1 and V2 terminals, we would still see twice R naught in parallel with twice R naught. So we're going to get an output noise spectral density that is 4 kBT twice R naught in parallel with twice R naught, or 4 kBT R naught. So eliminating that DC offset contribution of our output signal. The trade-off there is that we've increased our power consumption and we've increased our thermal noise at our output, which we can refer to the input and all that kind of good stuff for our measurement, all that kind of jazz. But anyway, so let's look at a slightly different way of implementing a Wheatstone bridge configuration. I'm on the wrong page here, so I'm doing the wrong thing. So this should be R naught plus delta R here, R naught, and then R naught plus delta R here. This is still going to be V2. This is going to be V1. I'm using voltage division. We're going to get away from our Taylor series expansion here. We'll see in a moment. We have V2 will be VDC times R naught plus delta R over twice R naught plus delta R. V1 is going to be VDC times R naught over twice R naught plus delta R. And from here, our output voltage V2 minus V1 is going to be VDC times delta R over twice R naught plus delta R. If I do a Taylor series expansion on this fraction, what I wind up getting is 1/2 delta R over R naught times VDC, or 1/2 pi L TL plus pi T TT times VDC after I throw away my higher order terms. So effectively, we have doubled the magnitude of our output voltage using this particular scheme, right? So with a previous scheme where we only had one work resistance, our output was 1/4 times pi T times the DC voltage. And in this case, we have it as 1/2. So we get a larger output signal for the same power consumption. So let's look at that really quickly. Our DC power consumption is still going to be the square of our DC voltage times twice R naught in parallel with twice R naught, or VDC squared over R naught. And our noise spectral density is going to be the same thing as it was a moment ago, 4 kVt times twice R naught in parallel with twice R naught, which is 4 kBT R naught. So we have the same power consumption as the previous example. We have the exact same noise spectral density at the output as the previous example. So what changed here? What is the trade-off that we're seeing here? An increase in complexity of establishing this thing, because we've got to have two identical piezo resistors under strain for it to work like this. Okay. So there is always a trade-off here. We get twice the output signal voltage, but it's physically harder to implement in our system. Okay. All right, so the last one that we're going to look at is effectively this exact same differential configuration, but we use a DC bias current. So I have IDC here. R naught plus delta R. R naught. R naught plus delta R. And R naught. Here is V2. Here is V1. Using Ohm's law, the quantity V2 is going to be what? Let me tease you guys with some trivial circuit analysis. So it won't be IDC because our current IDC is going to split. Right, exactly. So it's going to be half IDC. So even though these two branches, the order of the resistors are different, their total series resistance that they have is the same. So our bias current is going to split evenly between the two of them. So this is going to look like half IDC times R naught plus delta R. V1 is going to look like half IDC times R naught. And so our output voltage at the out is just going to be 1/2 IDC times delta R, which comes out to be 1/2 IDC R naught pi L TL plus pi T T. Okay. So in this particular configuration, and we'll get to the power and all that kind of stuff in a moment. Our output signal is just linearly proportional to our applied stress, which is fantastic, but we haven't eliminated that temperature dependency. So this is the type of system you would use if you had a very temperature stable configuration and you needed to amplify your output signal. Okay? Because we don't have a DC contribution, we just have our contribution that's due to the change. All right, noise, or excuse me, power and noise. So this is going to be IDC squared times 2R naught in parallel with 2R naught, which is just IDC squared times R naught. So the exact same power level as the very first sensing scheme we dealt with, and a similar noise spectral density. Vn will be root 4 kBT twice R naught in parallel with twice R naught. My handwriting is getting worse the longer the day goes. Or square root of 4 kBT R naught. So these are the different types of measurement schemes that you usually see with piezo resistors. Obviously, you could move resistors around and all that kind of stuff. So what I mean by that specifically, if we swap the position of R naught and R naught plus delta R and this expression, literally the only change we're going to get is that our output signal will be negative. And the exact same thing for effectively all of these, right? If we came up here and we put the R naught plus delta R up here, we're going to wind up getting -1/4. If we put the R naught plus delta R up here, the positive sign right here winds up becoming negative. So there's no point in actually going through and doing all those. It's a waste of time when the only effect is literally just going to change the polarity of the signal or the portion of the output voltage that is proportional to the applied stress. All right, so scrolling all the way back down to here. Now let's talk about noise in piezo resistors. And we've already done a little bit of this. So should hopefully be inherently obvious now that all of these sensing schemes introduce some amount of noise into our system because resistors, by definition, are thermal noise generators in our systems. So we are going to ignore our thermal noise at this point because that is literally just the root for KBT-R equation that we've been dealing with over and over and over again. And we're going to talk about other things that contribute to noise in a resistive system. So the first thing that I want to talk about is the shot noise. Okay. So shot noise is due to random fluctuations in electrical current across a potential barrier. So where shot noise might exist in a piezo-resistive system is effectively when we implement our wires that connect to our piezo resistor, there can be some small contact potential because we have a metal semiconductor junction, right? So if we deposit a wire onto our semiconductor-based piezo resistor, and we have an ohmic junction, we will have some small potential barrier, typically on the order of 0.2 volts to 0.4 volts. Sorry, I'm distracted by that thing. No, it's fine because it's hot outside. Yeah, so because there is an opportunity for a potential barrier there, when we have a metal semiconductor junction, we are going to have some shot noise. Mathematically, our shot noise is going to be a noise current spectral density, I sub n, that is given by twice Q, where here Q is the charge of an electron, times our current. So let me write some things here. So this Q is charge of an electron, which I'm 99% sure we've already introduced, but I'll write it down just for the sake of argument. 1.602 times 10 to the negative 19 coulombs. And then this I is just current flowing through our piezo resistor. Really, it's the current passing through the contacts in series with the piezo resistor, but it's the same current. For comparison's sake, we could convert this into a noise spectral density, or excuse me, a noise voltage spectral density. Vn will just be In times R using good old Ohm's law. And so that's going to look like 2Q I R squared, where I'm moving the resistance under the square root sign. All right. So let's look at a simple example here. Let's say that we have a piezo resistor whose nominal resistance is 1 kilo ohm and whose biasing current is 1 milliamp, and we are going to determine our thermal noise and our shot noise and see how they compare. Okay. So for our thermal noise, our noise voltage spectral density is the square root of 4 kBT R. So that's going to look like the square root of 4 times 1.38 times 10 to the minus 23 joules per Kelvin. We're going to assume room temperature 300 K. And then we have 1,000 ohms, where an ohm is a volt per amp and a volt is a joule per coulomb. So joule per coulomb multiplied by amp is a coulomb per second. Just getting the units here to work out right. Sorry. Yeah, so we're going to have, make this obvious, this is a coulomb per second because that's per amps. And so we're going to have joules squared per coulomb squared, which looks like volt squared times seconds. And so we wind up getting 4.069 nanovolts per root hertz as our thermal noise spectral density. For our shot noise,
Question as far as this goes. So when I run this direct calculation on calculator, I might have an exam. The closest it gets to is 4 nanovolts. Just, I mean, is that good enough?
yeah, absolutely.
Because I don't think I can get it to extend it past.
Yeah. I did this with MathCAD, so it's just got probably more significant figures in Boltzmann's constant. So 4 nanovolts works for me. I mean, this is,
It's not 4 microvolts, which is good. So
yeah. All right. So for our shot noise, our noise spectral density, and we're making it a voltage noise spectral density so that we can do a apples to apples comparison here, is going to look like 2Q I times R squared. So that is the square root of 2 times 1.602 times 10 to the negative 19 coulombs times our current, which is 1 times 10 to the minus 3 coulombs per second. And then we have our resistance, which is going to be 1,000 joules per coulomb multiplied by seconds per coulomb, and we're going to square that. And we should see once again that we get joules squared per coulombs squared times seconds, which is volts squared seconds. Yeah. And I get 17.9 nanovolts per root hertz after I take the square root of that. Stephen, for you, I'm going to guess it's going to come out to real close to 18, which.
Exactly 18.
Yeah. So. Sorry, brain fart here. So in this particular case, we have a shot noise that is 3.5 times this, or 4.5 times greater than our thermal noise. Okay, so this is something that can significantly contribute. The best way to eliminate shot noise is to not use metal to deposit wires. Instead, make your wires out of very heavily doped semiconductor regions as well. I think we talked about the advantages of this previously, but since so the semiconductor material obviously is going to have some piezo resistive effect, and we are implementing our piezo resistor as a semiconductor, and then we are implementing our wire as a semiconductor. Well, as we dope beyond that 10 to the 17 threshold, our piezo resistive coefficient goes down. So the portion that would be acting as a wire, its resistance is going to change less due to the piezo resistive effect than the resistor part will. So we also won't have a potential barrier to speak of, because we don't have a difference, or we won't have a contact potential to speak of, because we don't have a difference in materials that we are overcoming. So if we make our wires out of the same semiconductor, just using a different doping concentration, we should see that our shot noise is effectively non-existent. Now, this brings us to our third type of noise. Because we are making these piezo resistors out of semiconductor material, we are also going to have 1/F noise, where we talked about that previously. 1/F noise occurs mostly in electrical systems, specifically with semiconductor materials, due to dangling bonds and the random trapping and releasing of electrons as they migrate towards those dangling bonds, right? So for our 1/F noise, in our piezo resistors, mathematically, this is going to be given, the noise spectral density Vn is given as the square root of alpha times voltage squared divided by frequency times n, where I'm going to tell you what all this stuff means. So alpha is the Hughes factor. Okay. So this is typically on the order of 10 to the -5. It's a unitless quantity. V is the voltage drop across our resistor. F is our frequency, and N is the total number of carriers, charge carriers, in our piezo resistor. So, as the last thing that we're going to talk about today, let's determine the corner frequency for a piezo resistor. Having dimensions of, so we have a length of 40 microns, a width of 5 microns, and a thickness of 2 microns. Our piezo resistor is doped with ND is equal to 10 to the 16 atoms per cubic centimeter. And has an electron mobility of mu n is 1,250 centimeters squared per volt seconds, and has a Hughes factor of alpha is equal to 3 times 10 to the minus 5. We are going to assume the voltage drop across the resistor is 1 volt. So I'm going to give you guys a question here. It's been since before the break. What does the corner frequency represent here when we're comparing 1 over F noise and thermal noise? So just as a quick recap, right? So this is frequency, and this is noise spectral density as a function of frequency. So our thermal noise is effectively constant. Our thermal noise spectral density, let me say that, is constant. Our 1 over F noise spectral density obviously depends on frequency. And as the name suggests, it's going to look something like this. Actually, let's call this the log of frequency so that I can draw a straight line instead of trying to draw the 1 over dependency. Our corner frequency is the frequency at which our magnitude of our spectral densities are equal. So if we are trying to find our corner frequency in this case, we need to set our thermal noise spectral density equal to our 1 over F noise spectral density and then solve for the quantity F. Does that track? Okay. So if I have the square root of 4 kBTR is equal to the square root of alpha V squared over F times N. I can get rid of the square roots on both sides, and solving for my corner frequency, which is where these two things are going to be equal, gives me alpha V squared over N times 4 kBTR. Algebraically, that makes sense. So we now have a simple mathematical expression that we can use to calculate our corner frequency. What pieces of information are we missing to apply this thing? Alpha was given to us. V was given to us. Boltzmann's constant KB is a constant, so it's effectively given to us. We're going to assume that our temperature is 300 Kelvin. So the two things that we need to know to apply this equation are N, which is our total number of charge carriers, and R, which is the nominal resistance of our resistor. So which one do we want to figure out first? N. So since you suggested it, how are we going to do it, Hayden?
Well, we have in the.
Yep. So N is going to have some relationship with the number of donor atoms. I agree with that. What else?
Well, represents the number of electrons and the number of holes. Is going to be the intrinsic carrier.
Well, so N, if we're dealing with silicon here, well, so let's just make that assumption because we've been dealing with silicon the whole time, right? Silicon has an intrinsic carrier concentration somewhere in the ballpark of 10 to the 10 electron hole pairs per cubic centimeter. Since our dopant concentration is 10 to the 16, I would argue that this is a very N-type section of crystal, and so we can neglect our whole concentration without losing any real information.
Yeah.
So let's just deal with the ND, right? So effectively, if we have ND, that's the number of electrons per cubic centimeter. So now we simply need the volume of our piezo resistor. The concentration times the volume will give us the total number of carriers. Does that seem reasonable? Where our volume is just the length times the width times the thickness. So 10 to the 16 electrons per cubic centimeter times, did I say it was 20 or 40? 40. 40 micron times 5 microns times 2 microns. And then obviously I would need a conversion factor as well. So I have 1 centimeter in my numerator is 10,000 microns, and I would need to cube it. And I believe I get 4, oops, screen moved on me, times 10 to the 6 electrons. Math checking out, Stephen? Good deal. All right, so I would argue that calculating N for a rectangular resistor is going to be pretty straightforward. It'll be annoying if I gave you a serpentine or something like that, but it's not an insurmountable thing. Simply the carrier concentration times the volume of whatever shape the resistor has. Okay. Now let's talk about the resistance R, right? So we know
That might be off by, it might be 40. I'm getting an extra zero on it somewhere.
I don't know. I'm going to leave it as this. Yeah. That's what calculators and computers are for. So resistance. That is typically expressed as resistivity times length divided by cross-sectional area, right? So resistivity times LR divided by WR times TR, where we're assuming that our current here is flowing down our longitudinal direction of our resistor, which would make the most sense. How do we get resistivity?
One over conductivity.
1 over conductivity, and our conductivity is,
And comes in. Or ND. in this case.
Yeah.
We're going for it.
absolutely right. So this is going to look like Q mu n ND inverse of that, because Q mu n ND is our conductivity. The inverse of our conductivity is the resistivity times LR over WR TR. And because my hand's getting tired, I'm not going to write down the numbers here. I wound up getting 19.975 kiloohms. If I plug this result and this result into my expression up here, I find that my corner frequency comes out to be 22.673 kilohertz. All right, so I believe that is enough out of me for today. I have received a couple of questions about the exam, so I want to say a couple of things first. I believe I need to upload a homework assignment regarding capacitive sensing and piezo-resistive sensing so that you guys have some expectation of the type of problems that you might receive on your test. So my goal is to do that sometime tomorrow afternoon after I wrap up all my conference calls with Entergy over the next couple of days. Our exam was, I believe we had talked about potentially having it this Friday. Well, that is not going to happen because we did not cover the material due to it taking me 2 days to cover this piezo-resistive stuff and the technical difficulties that we faced on Monday, which I am quite thankful are resolved. So on Friday, I believe we are going to talk about piezoelectric sensing. And I think that will be the last topic that we are going to have. So I would like to endeavor to have our exam next Friday. So 1 week from this upcoming Friday, because that will allow you guys time to process the material and all that kind of stuff, work on homework problems associated with the different types of sensing. And then our exam is going to cover material from what we started with all the way up to this. I believe I said in the syllabus that we are going to have an in-class portion of the exam as well as a take-home portion of the exam. I still intend to do that. I think the in-class portion of the exam will likely be more theoretical concepts, and the take-home portion of the exam will be more solving things and all that kind of stuff so that you have time to think about things. I'll probably give you guys, I'll go through the notes and just make out possibly just a list of questions and stuff that I might put on the exam, and then I will pick some number of those to be your in-class portion so that you have some idea of what I'm expecting you guys to know. What was your question going to be, Stephen?
I was just gonna be, if you could, get the, if you're recovering now the lecture videos uploaded.
Yes.
I recall a lot of the theoretical material you didn't write down because it was just in class discussion.
Okay, fair. So I will endeavor to get those up over this long weekend as well as a kind of study guide for the type of questions that I might ask you so that you have a reasonably good chance of knowing exactly what's going to be on the exam so that you know what to write down. Kind of thing. Yes, that's correct. So this upcoming Monday is the MLK holiday, which means we won't have class because the university is closed that day. So this upcoming Friday, we're going to talk about piezoelectric sensing. The following Wednesday, we will wrap up piezoelectric sensing or talk about new material, depending on how far I get through piezoelectric sensing. This upcoming Friday, and then Friday, just to be very clear, the 20th will be our exam. So are we all on the same page? Good deal. All right, well, we'll see you guys on Friday.
Also, you're not.
Oh, it fell out. Sure. Let me see what's going on in chat here. Okay, so that's Jack. Okay, Jack was one of the one that was asking about the test, so just wanted to clarify.